Okay, we're live. Hannah, you can introduce the speaker, please.
Okay, well then, first of all, welcome back everyone to the summer school, and I will take over the moderation part for this afternoon session. And yeah, I would like to introduce the next speaker, and that is Gerard Höveling. And Etza started already introducing him in the morning, but that was a bit too early. So I continue now. So he's a professor in pedometrics and digital soil mapping at Wageningen University. And in his work, he focuses on the development and application of mathematical and statistical techniques to model spatial temporal variability in soils. And his tutorial today will be on design-based methods for assessing map accuracy, and I'm much looking forward to this session. So Gerard, please go ahead.
Thank you, Hannah. Thank you for your really nice introduction and pronouncing my name so perfectly. That's like really good. Let me start by sharing the screen. Okay, so that should be fine, I guess. Yeah, thank you also to Etzer and you, Hannah, for inviting me and Tom to give a lecture at the summer school. Yesterday, we learned that the summer school is already like 15 years going on. And in the early years, when it was, I think, still called the Geostats summer school, I was involved, but I haven't been contributing the last 5 years. So I'm really happy to be back. And also welcome to everybody watching this lecture. Thank you for taking the time. And we'll be talking about assessing map accuracy during this lecture. And there's a lot I want to tell you, so better get started. If you have questions, put them in the Mattermost chat, and Hannah will collect them. And hopefully we'll have time towards the end to answer them all and to address them. If not, I'm sure I will do that afterwards. Okay, so yeah, design-based methods for assessing map accuracy. And I'd like to start with a classical problem from statistics and probability theory. Maybe you remember that from when you took your statistics classes. So we have a vase here with red and gray balls, let's say. And I'd like to know, what is the percentage, the proportion of gray balls in this vase? Well, what we could do is, of course, check them all and just count them. And then we would know exactly what's the proportion of the gray balls in this vase. But that's a lot of work. So what we usually would do, and I hope you agree with me, is we take a random sample from the vase. For example, we could take randomly 30 balls from this vase and count how many of them are gray. And well, if let's say 10 out of 30 are gray, then our estimate of the proportion of gray balls in the vase would simply be 1/3, 1/3. And well, that's the way we do it. And it will give us an unbiased estimate of the proportion of gray balls in the vase. Now, suppose we have all gray balls on top in this vase and all the red balls in the bottom. Well, that really doesn't matter. If we do a random sampling of, let's say, 30 balls from this vase, then it still works because we take a random sample. It really doesn't matter the structure of the balls within this vase, whether they're on top or in the bottom. Every ball has equal probability of being selected, no matter where they are. So it would still produce an unbiased estimate because we take a random sample. And if we would not have a vase, but we would replace it with a two-dimensional surface, and we would distribute those balls over that two-dimensional surface, and we would randomly select 30 of these balls and count how many of them are gray. And we would use that as an estimate of the proportion of gray balls for the whole surface. It would still work because we take a random sample. And even though there is like a spatial structure in here, and the white balls are mostly over here, and here there are none of them, it really doesn't matter because we take a random sample. And if we take a random sample of 30 balls, maybe some of them will be really close to one another, but that really doesn't matter. The theory is still valid of sampling theory. I'm trying to illustrate that now with you with this example, but we'll come to talk about it a bit more later. So even if there is spatial structure, it doesn't matter because we take those balls, this sample, randomly. And you can imagine, you know, we are now talking about white balls and red balls, but could also be that every ball is a grid cell in our area of interest. And white means that, gray means, sorry, that the grid cell, the land use was not correctly classified, and the red balls means a correct classification. So basically, we can estimate the proportion of grid cells in the study area that are correctly classified by taking this random sample, and it will produce an unbiased estimate of the map accuracy. Well, correctly classified, yes or no, that's like a categorical variable, but we could also do this for continuous variables. Like, for example, you notice that all those balls they're all a bit different. So some are big, some are small. So if we are interested in the average size of the balls in this population, in this two-dimensional surface, we could take a sample and use the average weight, average size of that sample as an estimate of the population of the whole area. Even if every ball would have a number written on it, like the map error, or the error in your map at that location, or maybe the squared error of your map at that location, we could estimate the mean error and the mean squared error for the whole area using that random sample. Well, this was just like a teaser example showing you that probability sampling and the associated design-based statistical inference also works when you sample a spatial area, like in this example, even if there is spatial structure. And that is one of the aims of this lecture. I want to show to you, demonstrate that probability sampling and design-based statistical inference are a sound and solid methodology to assess map accuracy. So the example was just like a teaser, and we'll go at we go into a bit more detail of that in the next slides. A second aim of this lecture is that I want to explore together with you, how can we assess map accuracy in a case where we don't have a probability sample. So the aim one assumes, and that's the downside maybe of this probability sampling and design-based statistical inference, that you are able to collect a probability sample. And maybe that's not always realistic. So we also want to look at aim number two. But let's start with aim number one. Yeah, so we're talking about map accuracy. And then when we talk about map accuracy, of course, we need to quantify it. So we need to define it in some way. So today, I think we're only going to look at one metric, one measure of map accuracy, which is called the root mean squared error. I think, for continuous variables, that's probably the most common measure of map accuracy. But everything I'm going to tell you today could also work for the mean absolute error or the mean error, etc. So how do we define this root mean squared error? Basically, we have a variable of interest, z, which is a function of location x. X is some location in our geographic domain D. So let that be our variable of interest, and let's call that the reality. But we don't know that reality. We have actually made a map of that reality, z hat. And the map is available to us everywhere because that's what we've got. And we like to know how good, how accurate is that map? How close is it to the reality? So what we could do is visit all the locations in our study area. So I discretized the geographic domain D into a very large but finite number of, let's say, grid cells. And I visit all those grid cells. I subtract the map estimate from the true value, and I look at the squared difference, and I average those, and maybe I take a square root of that to get the root mean squared error. I think you're all quite familiar with this. Now, and this is what I call the population root mean squared error, because it really visits all grid cells, all locations in the study area. So this is what we want to know, but this is usually what we don't have it, right? Because in order to compute this population root mean squared error, we would have to know z at each and every location in our study area. And we usually don't have that. We will use a sample where at validation points, lowercase n, where lowercase n is much, much smaller than capital N, uppercase N, the whole population. And we hope that our sample root mean squared error is close to the population root mean square error. And let's look at a synthetic example where and check how all this works out if we use simple random sampling from the population. This is the map that I've got. And for those of you who looked at the question, they should be quite familiar with this map, because that is actually the exercise that I posed you with. So you were asked to estimate the population root mean square error for this case. This is the map. I gave this map to you, but there was also a reality, a truth, which, because it's a synthetic example that I had created. And from this reality, I had created a map, but you didn't know the reality. But if you know the reality, you can subtract the map from the reality, and this is then our map error. And of course, we can also take the square of those map errors. And the goal is that we want to, if we want to go for the root mean square error, we want to know what is the spatial average of this squared error. And that spatial average, the mean squared error, is 7.305. And if we take the square root of that, we get the root mean square error is 2.703. So for those of you who made a question, you know already now that this is the answer that we were looking for, and you were trying to get as close as possible to that from the, the data that were available to you. And we'll come to that at the end of the lecture. Okay, so this is what we want to know. And now let's go to R and explore a little bit how it would work if we would use a simple random sample to estimate that root mean squared error. So let me just show this to you. Okay, I'm not really good at using R, and I'm a bit old-fashioned. I'm still using SP rather than SF, so forgive me for that. Okay, and let's plot that map of the errors. So it takes a bit of time. But this is the error map, and let us now sample randomly 50 points from that area, okay? And let's plot those points on the error map. Okay, so every circle is one of, the center of every circle is one of the points that were sampled, 50 points in total. It's a random sample from the population. We do an overlay. We take the square root of the squared errors, and then our estimate is 2.878, which is not that far away from the true population root mean squared error. But it's only an estimate, huh? And we can do it again and take another sample. And then we will, of course, have different locations because we randomly take another 50. Okay, now they're elsewhere. And so we also get a different estimate. A little bit further away, when you use a sample to estimate the population root mean square error, you will always have some estimation error. Note, by the way, that some of those locations are really close to one another, right? But that really has no effect, doesn't matter. It's still a random sample from the population. So let us explore now if we not do it only once or twice, but we actually do this 1,000 times. So 1,000 times taking a sample of 50 points and estimating the population root mean square error from the sample. So that's what I do here in this for loop. And let me then plot a density of the 1,000 estimates that I get. Okay, so this is the distribution of those 1,000 root mean square sample values that are estimates of the true population root mean square error, which is the dashed line over here. So actually, well, that's, what I mentioned earlier today at the start of the lecture, we get an unbiased estimate. So every sample root mean square error is, is not spot on with the population root mean square error. Sometimes it's too high, sometimes it's too low, but on average, we get it right. That's this idea of root mean, that it's being unbiased. So the average of those 1,000 is already very close to to 2.703. And if I would do an infinite number times rather than 1,000, it would be exactly equal. Now, what would happen? What would change in this distribution if we would not take 50 points as a sample, but we would take 100 random points from the area? And that's where I need your input. So let's go to Mentimeter, and I'm going to ask you to submit your answer. So please answer this question. What is the effect of increasing the sample size from 50 to 100 and using the average of 100 random points in the area to estimate the root mean square error? And you have a choice of 4 possible answers. And I hope it all works. So you have to go to menti.com and use this code to submit your answer. Ah, okay, good. We already have 1 response.
Maybe copy that code to the chat.
Yeah, of course. Let me see. How do I get to the chat? I don't know. Don't seem to have access to the chat. Or maybe here. Separate window. But of course, everybody can see it also on the screen. I hope it's not too small.
You just copy the numbers, I think, Gerard. You didn't copy the URL.
Oh, well, it's menti.com. Okay, I can type that here.
Okay, that's it.
I need to pay attention to the clock. Time goes fast.
I'm seeing some skew distribution.
Yeah. So the majority actually thinks there's no effect. Whether I take a sample of 50 points or 100 points, it just doesn't really make a difference in terms of how accurate that distribution of the sample RMS is. How close is it to the population? But there are also people who say, well, actually, it does have an effect. Well, this gets very little votes, but here this is about equal. Well, why don't we have a look? I'll leave it open. Maybe there will become more. So let's simply do it. Okay. So now I take each time a sample of 1,000, and I do the 100 points, and I do that also 1,000. And let's plot both distributions in one graph. So the blue one is the one we had with 50, and the green one is the one we have when we use a sample size of 100. And actually, you do see that it gets narrower. Our estimates becomes more accurate. And I think you should all agree that this makes sense, because the larger your sample, the closer you are to what you want to know, because you have more information. How much better did we get? Well, 70%. So basically, we were able to reduce the spread of the distribution by 30%. So answer B was correct. Okay, let's go back to the lecture. So, well, maybe I'll just, oh, wait a minute. So this was the correct answer. So, well, it's actually a small group of people who got that right.
But the RMSE, the mean RMSE stays the same, more or less.
The population RMSE is constant, of course.
People confused with that.
Yeah. Okay, maybe, you need to think about it a bit, and then maybe it will become clear. Maybe watch this lecture once again, and then maybe a bit. Well, let's continue. Okay, so what have we learned from this example? Random sampling produces an unbiased estimate of the population RMSE, because the center of that distribution is centered on the population RMSE, and the uncertainty of the estimate, how close is it to the true population RMSE, decreases when the sample size gets larger, gets bigger. So of course that's good. But actually the decrease is inversely proportional to the square root of the sample size. This is really something basic from statistics, and maybe you remember that from a course that you took a long time ago. And it's actually bad news, the square root of n, because it means that if we want to double the accuracy, we have to quadruple our sample size. So it would have been preferred if there would be an n here, but that's simply not the case. Okay. If our sample size is large enough, then we have the additional property from the central limit theorem from statistics that error, the estimation error, is approximately normally distributed. And so we can compute confidence intervals, like, for example, the 95% confidence interval. And I have an example here from a PhD student of mine, Anatol Helfenstein, who took the summer school last year, by the way. This is the pH of the soil predicted in the Netherlands, and we used a probability sample to estimate the root mean square error of our maps for various depths. So the black disk is the estimated root mean square error, and then those gray bars over here, they show the 95% confidence interval. So we can be 95% confident that the true population RMSE is within these limits. So it's all quite nice, I would say. So the summary of the first aim of this lecture is that we can apply probability sampling and design-based statistical inference to assess map accuracy. There's no problem with the fact that actually some of those points are really close to one another because it's still a random sample from the population being the whole map. If you are not convinced, and that may well be, then maybe check this paper. Actually, I'll show that paper later. And, you know, I didn't share the PowerPoint, the presentation yet with you, but I will do so after the lecture. So then you can also click on this and it takes you directly to that paper. This is another paper. Actually, it's this paper by Dick Bruss. You also see Dick Bruss's name over here. He is really a spatial sampling expert, and he should have been giving this lecture, but he retired. And he said, well, Gerard, why don't you take over? So that's why I am here now. Okay, anyway, so this goes into very much of the details of that. So if you're not convinced, you might want to check this. We get unbiased estimates and we can compute confidence intervals. All really nice. Now, it's not only simple random sampling that you can use. You can also, for example, use stratified random sampling, cluster random sampling, systematic random sampling. But of course, there has to be a random element in there somehow. So it has to be a probability sample. So Dick wrote a book, Spatial Sampling with R, and you can access it here. It will be released really soon. And the PDF of that book is free for everyone. So I can really recommend that. Okay, good. Aim 2. What do we do if we don't have a probability sample? And that, of course, happens quite often, right? So in practice, we usually cannot afford, or maybe we don't think about it. Maybe we should reserve 5% of our budget for validation and taking a probability sample. But if we didn't do that, we'll have to still want to estimate the map accuracy. And if we don't have a probability sample, we cannot use probability sampling, design-based statistical inference. So what do we do? Well, what we often do is maybe use data splitting, right? We have a data set for mapping and we split it into a part for calibration and prediction and another part for validation, or we do cross-validation. I think all of you will be quite familiar with that. Well, what's best? What should we do? So another poll, another bit of interaction with you. Let me see if I can go there now. So which of these 4 methods would you prefer? So again, go to www.menti.com and use this access code. I can maybe copy this to the chat again. And wow, cast your vote. Okay, it's nice to see responses. And it seems that most of you prefer tenfold cross-validation.
Is that with the with refitting or without refitting?
Whatever you like, Tom.
Well, it's a very
Of course,
different. It is
of course, you
different.
fit your model with 9 of the 10 folds, right?
And then you refit 10 times. So.
Each time you fit again, so you have to do it 10 times. And here, in leave one out cross-validation, you have to do it n times, right? Where n is the number of observations. So this is much more computationally, much more demanding, I guess. Yeah. So maybe that's the reason why people prefer this. Okay, so yeah, let's go back to the lecture. So I'll leave this open and see what the preferences are. And let me tell you what I prefer. Let's see. Yeah, okay. I think that usually cross-validation is better than data splitting, because data splitting very much depends on the split that you happen to make, right? And actually, if you do k-fold cross-validation, and maybe we should talk about a little bit more the details, like Tom is interrupting me about how exactly, what do you mean by this? But basically, you know, when you do k-fold cross-validation, every observation is used once for validation. So you use the whole data set for validation. That's what I like. You don't get that when you do data splitting. And then I think normally I would prefer a little bit more leave one out cross-validation over k-fold cross-validation, at least if you can afford it computationally, because you know you would be closer to the final modeling that you would do using all the data. And you just drop one observation when you evaluate how well did you do. Maybe also a little bit depends on the case. And yeah, and there's one important problem with all these 4 methods that I offered to you, is that when we do cross-validation or data splitting in case of clustered data, and I really should refer here to Hannah's lecture from yesterday, where she made really, really clear, very well clear, that in case of clustered data, yesterday, the Münster was removed from the calibration data set, and you try to predict that Münster. Well, maybe that's even an extreme form of clustering where you actually are extrapolating very much. Then, yeah, there are some problems when you have very strongly clustered data and apply cross-validation. For example, if 90% of your data are in 10% of the area, then if you use a standard cross-validation to estimate the map accuracy, then this will be 90% dominated by how well you do in 10% of the area. And of course, that's that part of the area where you probably do much better because you have a large, high sampling density in that area. So that would not be fair. You are too optimistic. Right. So we like to compensate for this effect. The fact that standard cross-validation and also data splitting randomly wouldn't do a good job, wouldn't provide an unbiased estimate, a reliable estimate of the map accuracy in case of clustered data. And clustered data happen a lot. For example, here, I just went to the internet basically and look at some examples. This is air quality network from the European Environmental Agency. So we have a lot of stations over here, but hardly any over here. And probably air quality here is pretty good. So if you use this sample to estimate also the errors in our maps, well, I don't know how that differs, but if there's little spatial variation, you probably do better mapping over here than you do over here. So it wouldn't be very fair to use a random cross-validation. And this is above ground biomass as an example. And for example, well, here in the tropics, but you have a lot of data from Mexico and this part of Central America, but very few from Brazil. And here, Australia, hardly any. And well, so, another strong case of clustering. And these are data that I work with myself, soil data distributed all over the world. So there's a high sampling density in Europe and in the US. We have almost no data in this part of Australia, in Siberia, Sahara, Canada. So yeah, clustered data occur quite a lot. So what can we do in case of clustered data and we have to do a cross-validation? Well, what some solutions? A spatial cross-validation that's often used or proposed. I think you have to be very careful with that because it's starting from the wrong premise that spatial autocorrelation should be avoided. But I hope that I've made clear with the first aim of my lecture that actually, as long as you take, for example, if you take a random sample, some points will be really close to one another. It's not a problem at all because you took a random sample. So spatial cross-validation really avoids that. Make sure that never a validation point is close to calibration points, and then it tends to be too pessimistic. Density weighted cross-validation, basically somehow attach weights to each validation points depending on what's the density of the data in the local neighborhood. High density means lower weight. We're working on that methodology. Model-based cross-validation is basically you build some kind of a geostatistical model of the error or of the squared error in your map, and then you interpolate those, and then you take the average. Also, you know, I'm not going into the details of that, has to be developed. And maybe there were some suggestions from you, answers to the question that I had posed. Have a look at that in a minute, hopefully if we still have time for that. This is really a lively area of research. There's lots of developments, no perfect solution yet, as far as I can tell. So I hope that you will be able to contribute. Okay, so I recently published a short communication. It's only 5 pages in ecological modeling with Alexander Wadou as the first author, and also with Dick Brus. I already mentioned him before, and Sietse de Bruin. And we had a bit of a provoking title, I think. Spatial cross-validation is not the right way to evaluate map accuracy. So, and we really advocate, make use of probability sampling, right? Design-based statistical inference. And the core, well, we illustrate in this paper, we do have a case study. And I'd just like to show you the main result. So, okay, we took an area in the Amazon, and we needed to know the reality everywhere. So it's a bit of a synthetic case. We took an existing map of the above ground biomass as the reality, and then we took samples from that reality and we interpolated using a random forest. And then we checked how well did we do with 3 cross-validation methods, and also for 3 types of sampling designs. So let's start with this light blue case. And on the y-axis here, so you see all these box plots here, the y-axis is the error in the estimated mean squared error. So we like it to be close to 0. So the blue one over here does a really good job. So if you have a systematic random sample, a regular sample, then standard random k-fold cross-validation actually does a pretty good job. And it also does a pretty good job in case of a simple random sample. But when you have a clustered sample, it's simply much too optimistic, right? So the thing we said before. So it's not doing a good job, standard k-fold cross-validation, when you have a clustered data set. Now, these two, the green and the dark blue, they are both versions of spatial cross-validation. And actually, in our case, they did bad jobs in all cases, especially the buffer leave one out cross-validation method. So they are too pessimistic, okay? Especially, this one over here. But even in case of a simple random sample, they just tend to be too pessimistic about the root mean square error. I also put the red one in over here. This is when you take a simple random sample from your study area. So not systematic random, well, actually like this simple random sample. So an independent data set using probability sampling, and what we usually cannot afford, but just to confirm that the red is doing a really good job in all those cases, centered on 0 with a pretty small standard deviation. And all these cases use the same number of observations to estimate the population root mean squared error. Okay, if you want to know more about this, I have put the link to this paper in the presentation. Okay, we have 10 more minutes. I'm not sure if
There
we'll
are
have
just a
time for
question
questions.
for the spatial. Which method you use the spatial cross-validation? Which
Okay,
method?
so
Block or
you read the paper, okay, Tom? And basically, we're using the methods developed by Ploton et al. So,
but do you know, is it a spatial block?
Tom, put your question in the chat and I'll answer it.
We have
Okay.
time. We have time until 1/4, so you have a bit more time.
Ah, wow. Okay. Yeah, that's good. So we actually do have time. Yeah, I just had 4 o'clock Dutch time in my mind. Oh, good, good. So in that case, yeah, Tom, so to answer your question, because I was a bit blunt, you know, spatial k-fold cross-validation, buffer, leave one out cross-validation. Yeah, I think they're all variants of what in general is called spatial cross-validation. So what do you do here? You have your complete data set, you make k-folds, and you make sure that those folds are, geometrically compact. So you have k compact clusters, and you remove one cluster and use all the other folds to estimate at that left out cluster. So basically you're doing a bit of extrapolation. It's pretty much the same as what Hannah showed yesterday. You leave out Münster and you use the rest of the area to predict at Münster.
Okay, no, that's,
and then you
that's
don't do
important
really a good job.
because there's about 3 methods to do spatial cross-validation.
Yeah, so I am referring here to what we used in that paper. And our paper uses a method, the methods used by Ploton et al. It's in the references of our paper, and they had 2 spatial cross-validation methods. And I'm trying to explain to you what we've used, what these are. So this one is where you stratify, and you define your folds by using compact geographic clusters. So not random folds, but spatially compact. And this buffered leave one out cross-validation is where you make sure you have a buffer around every validation point, and the buffer has a certain radius, and the radius could be derived from the range of the semi-variogram. So it's supposedly to have a lot of theory behind, but actually, well, we don't think that it is fair, because, whenever you do a validation of a map, the map predicts at points using calibration data that can also be nearby. So basically, when you do buffered leave one out cross-validation, you make sure that you never have a calibration point close to the validation point. It has to be far away because there's a buffer around it. And that's why it becomes very pessimistic, because it's actually always evaluating how well do I do if I extrapolate in geographic space rather than interpolate. Okay, that's all I want to say about that now. But the details are all specified in the papers that I referred to. Okay, right. So we have plenty of time. You might say, well, okay, maybe we have like 10 minutes to discuss, and then we also have still a lot of time for questions.
You have a lot of time, yes.
Yeah, the map accuracy question. So I think I posted that on Tuesday or Monday or Tuesday. And this was asking you, can you estimate the population mean error and the population root mean square error for a study area, which is a square study area? Well, we had a map of that, but you didn't know the reality. But what I did give you is for 1,000 points in that study area, the geographic coordinates, the X and the Y, and the error. And so what we want to know is the mean error and the root mean square error, but we want to know it for the whole study area. So I think the study area was 500 rows by 500 columns. So that's 250,000 grid cells, right? So this is defined for capital N equal to 250,000, because that is what we want to know. How well did we do for the whole study area? And you were asked to estimate the ME and the RMSE using a sample of only 1,000 points. And these were given to you. Yeah, and if you look at this sample design, I think everybody notices that there are some clustered data, right? It's not a random sample. There is some clustering there, and we know now that clustering is risky. So because if we would just take the naive default unweighted estimate of ME and RMSE, replacing capital N here, uppercase N, by the lowercase n, and just taking the average of all those 1,000 cases, then I think we should be able to do better, because we would give a lot of weight to those areas where we have a high sampling density. So we would like to, downgrade their influence and maybe pay more weight, give more weight to points that are not in highly dense areas. Okay, so that would be, but then there's also the model-based kind of approach. So I got 3 submissions from participants of the course. And so let's have a look at the answers that I got. So the true mean error is 0.6615. And the true root mean square error is 2.7027. So I got estimates of both of them. And I simply took the absolute difference between the true and estimated and added up those 2 absolute differences. And that gave us the criterion, because that's also what the exercise said over here. The contribution that has the smallest sum of the absolute ME and LMSE estimation errors is the winner. So let's see what we got. So if you would use an unweighted, naive kind of just let every observation is equally important, well, you would get a criterion value of 0.2032. Now, I got a submission from Carles, from Abdelkrim, and Olivier. And well, Carles, I really liked your approach, because you took this model-based approach where you said, let's build some kind of a Kriging model, a geostatistical model of the error and the squared error, and let's interpolate that and take then average for the whole area. But you did actually worse than the unweighted case. I don't know exactly why. I didn't look into the details, but I liked your approach. But in the end, your answers, your outcome was not as good as taking the unweighted case. Abdelkrim, well, Abdelkrim, you simply used the unweighted approach. You took the mean error and the root mean square error of the sample. And so you got exactly the same results as I had for unweighted, and you got exactly the same criterion. And then Olivier, I think Olivier submitted his answer this morning and also used a model-based approach, also quite good. And also you checked, and I think Carlos did that too, whether there were duplicates. And as it happened, I didn't do that on purpose, but actually in the data set over here, there were actually 7 or 9 locations duplicate. You don't want to count them twice, I think. So you took care of that, but somehow something went wrong, I think, in your code, because you got an extremely high criterion value. So I think the winner is Abdelkrim. Although I like Carles and Olivier's method more, in the end, the criterion is the lowest for Abdelkrim. So we also had a few out of competition submissions from Etzer and also from Sietse de Bruin. So I put them in gray here. I hope you can still read them. Because they don't really, they're not really participants of the summer school. So, and Etzer took both a design-based, very clever way by, he looked at the sum, said, well, there are clusters clearly. So let's identify the clusters and let's pay. So basically, it's a kind of a density-weighted approach. But also something must have gone wrong, I think, Etzer, in your calculations, because the RMSEs are very much too low. So that's why your criterion values are very high. And Sietse, I mentioned him because he's one of the co-authors of this ecological modeling paper, short communication. Yeah, he did better than the unweighted case, but not very much better. So in fact, this model-based approach, similar to what Carles did, and also Olivier, and also Etzer. But maybe Sietse took more time. He had also more time. I had shared with him the exercise already a few weeks ago. So he got the best. But they're out of competition. So I think for me, Abdelkrim is the winner. Okay, that's it. Thank you. And okay, now we still have like 15 minutes for questions. So I'm happy to answer any question.
Yeah, thanks a lot, Gerard. And I think it's good that we have 15 minutes left because quite some questions came up on MetaMost. Probably we start here at the beginning. So the first question is, while the simple random sample will give an unbiased point estimate, if there is a spatial structure, will a local neighborhood variance estimator be better than a spatial random sample variance estimate?
Okay, that's a long question. So basically, I think the question has several components, but the first is, why does simple random sampling give, maybe should I stop sharing? No.
Yeah, I think it's all right.
Keep sharing.
Keep sharing, yeah.
No. Keep sharing because we can look at the slides also.
Yeah, and should I go to, let me go to the slide, maybe this introductory example. I'm not sure if this is the right slide, but basically, we see spatial structure here, right? Let gray be wrong classified and red be correctly classified. But we take a random sample. So spatial structure has no effect because every of these balls has equal probability of being selected. So the gray balls have equal probability of being selected as the red balls. So if I want to estimate the proportion of gray balls, of balls that is gray in this population in the study area, if I take a random sample, that random sample will give me an unbiased estimate, no matter whether there is spatial structure, yes or no. I'm not saying that it's the best you can do, right? So maybe there are ways of doing a better job by taking the spatial structure into account. And maybe that is something we discussed later on in the second aim of this talk, like, can we do a better job? And then maybe I had a list. Yeah, maybe that could be this slide. So we want to estimate the population map accuracy. Well, if we would have a random sample, we would, the nice thing about that is that we have theory that tells us our estimate will be unbiased. And we also can quantify the estimation error. And I also mentioned that, simple random sampling is not optimal, right? Maybe if you have spatial structure, you would rather use systematic random sampling, or I think there's also like a compromise between design-based and model-based. So you can have I don't know, I forgot the name now, but Dick will know. So there's lots of ways how you can do better, but it's all still based on design-based statistical inference.
Model assisted.
Yeah.
Model assisted.
Model assisted. Thank you, Etzer. Yeah, model assisted inference. So there's lots of theory out there that can help you to do a better job than just simple random sampling. But the nice thing is that the theory stands and you get unbiased estimates and you can also quantify your uncertainty. Now, Hannah, what was the question again?
While the simple random sample will give an unbiased point estimate, if there is a spatial structure, will a local neighborhood variance estimator be better than a simple random sample variance estimate?
Yeah, so the first part of the question, I think I answered that with the simple random sample, you get an unbiased estimate. And well, I did the best I could to convince you. If not, we'll have to continue later on, or maybe you read some of the literature that I provided. It's simply because you take a random sample. Now, if you make use of this spatial structure somehow to do a better job, because you know that those errors are spatially, structured, and that's actually also what you do when you do this model-based approach, and that's for sure something you should be doing when you don't have a probability sample, then probably you can do better. And so that the methods could be like model-based or maybe density weighted. I have a problem with the spatial cross-validation because it's very hard to make choices there. You quickly overdo it. So we know that random cross-validation will produce too optimistic estimates of the map accuracy, but the spatial cross-validation, it can get really out of control, and you basically get much too pessimistic estimates, and there's no way of controlling that. So I'm not a fan of spatial cross-validation. Okay, well, that's probably the best I could do answering this question. Are there any more questions?
Oh, quite a few. So the next one is less complex, I think. Do you have a recommendation which metric to use for categorical maps?
Yeah. Well, the most common one I would say is the map purity. So let's say the proportion of area, the proportion of cells that are correctly classified, right? So it's some number between 0 and 1. And I think it was you, Hannah, who mentioned the kappa index yesterday, or, that's also something often used in the remote, that you compensate a little bit for the random chance of getting it right. You have these confusion matrices, right? And error matrices, and you have the consumer's accuracy and the producer's accuracy. So there's a lot, but if you have to use one number only, one metric only, I would go for the proportion of points that are correctly classified.
Okay, so the next is rather a comment, but maybe you want to comment on that comment. I'm a bit confused now about deciding between the random sampling approach and the spatial cross-validation approach that I suggested yesterday. I guess I need to relook at all the papers and think a bit more about it.
Yeah, and maybe I didn't do the best job I could explaining the difference. So this design-based probability sampling kind of inference is really based on statistical sampling theory, and it only works if you have a probability sample from your area of interest. And probability sample means that every location in your study area has a probability of being selected, and that those what they call inclusion probabilities. So you really have to do that in a proper, sound way. So you delineate your study area, you have a shapefile or whatever, and then you randomly or use or maybe stratified randomly. Well, all those kind of probability designs that you can use, you have to use probability sampling to select those locations, and only then can you use design-based inference. So, and then the second aim of the lecture was about, suppose you don't have it, which we often have in practice, then we cannot use design-based. I know that some people do. They say, let's just pretend that our data are a random sample from the study area. But I don't like that, because that's not true. You often have just a legacy data set, a convenience sample, which may be clustered. So it's not a random sample. And then we still want to estimate the map accuracy. And here are some methods that can do the job, but they all have pros and cons. So really, we need to work on this as a community, I think. Okay.
Okay, so next I squeezed in a question from my side. Keeping in mind that most data used for spatial mapping, at least those used for global mapping, are heavily clustered, and following the results of your paper, why isn't the title of your paper commonly used random and spatial cross-validation strategies are not the right way to estimate map accuracy?
Okay. So commonly, you want to put commonly used in front of this title.
So the commonly used random and spatial cross-validation strategies.
Yeah. Okay.
Spatial cross-validation strategy is not.
I think, Hannah, I think, I agree with you there that, this shows us that random cross-validation doesn't do a good job in case of clustered data, right? So the title says spatial cross-validation is not the right way, but random k-fold cross is also not the right way in case of clustered data. So I agree with you there, but I think, and it's a very good point, because many people do that, and I've done that myself too, and Tom has done it also. I remember, when we did this soil grids mapping in 2017, he said, these are our cross-validation statistics. But then the data were very clustered. So probably those RMSEs, they were far too optimistic, much too low, not really representative of the whole study area. But what we wanted in this paper, in this short communication, to really point to the fact that many people say spatial cross-validation is the solution. And we don't believe that, right? And we have here, well, this is a case study, an illustration that you can get strong biases when you have spatial cross-validation. So that was the thing we wanted to say, but I fully agree with you that standard, common, random cross-validation also will not be doing a good job in case of clustered data.
So maybe we need we need to come up with an alternative cross-validation approach then.
That's why I wrote this, right? Yeah. We're not there yet. I like this one, by the way. So, and we're working on a paper doing this, but this is also, but yeah. So there's a lot we can do still, and we need to do it. Yeah.
Okay, so there's another question based on your excellent talk. I would conclude that for the moment, the only accepted and validated method to map accuracy assessment of clustered data is taking a probability sample using the design-based approach. Would you agree with that?
Yeah, I agree with that. Yeah. So if you are in a situation where you calibrated a model to make a map with these kind of data, and you make your map and you want to evaluate how well did I do, then the best way would be to take a probability sample from your study area. Now, this is the Amazon, and I haven't been there. I think Alexander was there, and so the first author of the paper, and he did, really an excursion, walking in the wilderness, and we have many people from Latin America, from Brazil. I mean, the accessibility is really a problem here, right? So if I generate 500 locations and I say, go there and check what's the true biomass at those locations, that may be a costly affair. So that's, of course, also why so often we have clustered data when we calibrate models. But this is a risky situation to somehow evaluate the map accuracy using the existing cross-validation strategies. And maybe the weighted one or the model-based one will do a better job. But yeah, in all cases, I think probability sampling, design-based statistical inference is the best if you can afford it, because also it has theory backing it up. We can simply prove that the estimate of the map accuracy is unbiased, and we can quantify the accuracy of those estimates with confidence intervals. So it has so many nice properties.
All right, we have 2 minutes left, and there's another question. I think Tom also has another question. I quickly read the last question here from Mattermost. Does the selection between random sampling or spatial cross-validation not depend on the characteristics of the variables we are trying to predict? For example, if it's an ecological or biophysical variable that we want to map?
Yeah. So I think maybe spatial cross-validation or all the cross-validation methods that I mentioned here, they perform worse or better depending on the spatial structure and all that. But design-based probability sampling doesn't care at all what is the spatial structure. Like I tried to explain in the starting example, if we have this over here, okay, I have to go all the way back. If this is our population, half of the balls, the gray ones are on top of the red one. If we take a random sample, we still get an unbiased estimate. So no matter what the structure is, it makes no assumptions whatsoever about the spatial structure. It always works because the sampling is random from the population.
All right, then 1 minute left, Tom.
Okay, Tom, maybe. You have to unmute. Yeah.
Yes, I agree that if you strictly put these buffers, and you can, I mean, I think Patrick Schratz made this plot where the accuracy drops as you go more and more distant. So I agree about that. It becomes too pessimistic. But I don't know. I think maybe the title of your paper, I mean, your note, it might now tell people, like anybody who applies spatial cross-validation will say, well, I can reject your paper because these people said you shouldn't use it, right? So it becomes a bit, yeah, it becomes a bit a strong statement.
I think, Tom, this is science, right? So we are in a debate, and we are in a discussion, and we're trying to figuring things out. So I really welcome that. I like that. So if the others can prove that there's something wrong here, and or the actually spatial cross-validation is not so bad after all, or let's enter this discussion and write papers about why it is okay to use spatial cross-validation.
But I just want to say that the statements in this paper, they are not about let's explore. This is wrong. So
that's our position.
Yes.
Yeah.
I think with an eye on the clock, we should probably continue the discussion.
Yes, we have to stop. But it was a great talk, great demos, and I don't know if you can share the code also used for simulations.
Yeah,
please, and let's go to the next speaker, please.
And thanks a lot, Gerard, for that very great lecture. And then we move on, and I would like to introduce the next speaker, which is Jakub Nohozat, and he is an assistant professor at the Institute of Geoecology and Geoinformation at the University in Poznan in Poland, and he is a computational geographer working at the intersection between geocomputation and environmental science, and he is one of the authors of the book Geocomputation with R, which I guess many of you are aware of, and his presentation today will be about spatial segmentation in R. So, Jakub, I'm looking forward to your presentation, but we can't hear you yet. No, still not.
Okay, so maybe I can change them.
Great.
Yes.
Yeah, I changed the microphone, so yeah, that should be fine.
Good. So good.
Great. All right. So thank you for the invitation, and hello everyone. I'm Jakub, and today I will talk about new package and some other related packages about doing spatial segmentation in R. And in the following the previous lectures, I will be talking mostly about fairly new things and very new developments. So there is always something to change, add, and modify. So I will also look forward to the discussion and to your suggestions. So let's just start by making short introduction. So basically, often when we work with spatial data, we work with raster representation of the data, and this raster representation considers cells as their main object, but the cells, they often do not relate to actual objects in real life or actual processes in real life. And in this concept, we also can think about different cell size, that sometimes our cells are maybe too large or maybe too small to consider our objects or processes. And with this in mind, there is a whole group of methods that work on those kind of concepts called object-based image analysis. And in terms of spatial data, it's called GeoBIA, or geographic object-based image analysis. And the approach here is that before doing any other calculations or before doing any other steps, first we need to identify our true objects. And then if we identify the true objects, we should somehow add their meaning. So we need to classify them. And in this talk, I will mostly spend time on the first part. So how we can partition our space to identify homogeneous objects. And there are many techniques to do so. One of the techniques very often used is called multi-resolution segmentation. And you can see some examples of this segmentation on the right. But quite recently, more and more applications have been using an alternative approach of so-called superpixels. So with superpixels, the main idea here is that we first try to do so-called over-segmentation. So first we try to group very, very similar cells together, and those similar cells, they will create homogeneous areas. And you can see two examples here that we got new polygons, and those polygons are actually our superpixels, and those superpixels, they contain fairly homogeneous areas. And there, in the last 15 years or so, they've been few dozens of methods to create superpixels, but the most often used is called SLIC. And these methods of superpixels, they were mostly developed for images, and therefore for spatial data, they also most often used for images. So instead of using images from our cameras, we are using satellite images or similar. And this superpixel algorithm, it's very, very simple if we just go step by step. So it starts with regularly located cluster centers. So we can see here on the right that we've got some image. We put some cluster centers in a regular space. And this is one of the main parameters of this method, that we need to provide what's the interval, what's the distance between our centers. And then we need to calculate two distances. Because, for example, let's consider the center cell in the top left corner. So we need here to consider two things. Firstly, we need to consider spatial distance. So, for example, how far this cell is from this center, and how far this cell is from this center. So this cell is certainly closer, and this cell is farther. But also, the second thing we need to consider is the distance between values. So how similar our colors here are to this cell, or how different they are. And probably the cells here are more similar to the value in our center than the values here. And you can see this distance, the complete distance that you can see on the left, is basically a combination of our spatial distance. So this is our distance in these terms in Euclidean space, and our values distance. So what's in this context, what's the color distance between our center and all of the cells that we are comparing it to? And you can see we are using just a limited window to compare them to. So we are using window of 2 by 2s. So that's why we are looking just in some local window. We are not looking for the whole image. And that's why this method is often similar to being a spatially constrained k-means. So in the terms of the below example, this color distance is fairly easy. We just go through our color representation. So for example, if we got RGB representation, we are comparing R to R in our center, B to B in our center, and G and B in our center. And this is how we can calculate what's the color distance. While Euclidean space, it's just what's the distance in both dimensions. And that's why we can also think about those two values, those two distances, about that they represent some different things. So the color distance, it's about controlling how homogeneous our superpixels are. In other words, how much we care about similarity of colors. While the second one says how much we care about the closeness to the centroid of our cluster. So what we are doing now, in the next step, we are repeating the same process several times. So usually it's between 4 and 10 times. And in this process, we are just comparing our cells to the some closer centers, to the few closest centers, and we are assigning the value to the pixel based on the most similar center of the cluster. In other words, when the total distance, so this spatial distance and the value distance is the lowest, then we assign the cluster value. And with each iteration, our center can slightly move because we are our area is not square anymore. So that's why our center is also moves a little bit. And as you can see on this animation, the borders of super pixels can slightly change with each iteration, adjusting to different values in terms of space and colors. And the result that you can see on the left, it has one potential problem. Because this algorithm is very simple, it also doesn't care about connectivity. And that's why sometimes we can have cells like this one, which probably belongs to this or this cluster, but we never care about the connectivity. So it has the same value as this cluster probably, but it's not connected to the superpixel. That's why there is one optional step, which is called enforcing connectivity. And in this step, we are basically removing or merging the smallest areas that you can see here in the red, and we are merging them with the closest superpixels. That's why, in this way, we are sure that our all of our superpixels, they are spatially connected, and they occupy just one space. With superpixels, I mentioned that we've got an S parameter. So S parameter stands for the step or the distance between our initial centers. So for example, if this value is small, then we will have more superpixels. And on the other hand, if this value is larger, so here we have a smaller value, but if the value is larger, we would have smaller number of superpixels, and also each superpixel will be larger. And the second main parameter is called M, which represents compactness. So compactness is basically a relation between spatial and value distance. So if we want to maybe put more emphasis of the distance, spatial distance, this value should be larger. But if you want to put more emphasis of value distance, then this value could be smaller. And you can see here on the right, comparing to the one on the left. So the left one has slightly larger M value. So that's why we've got more big superpixels looking like squares. While on the right, this value is smaller. So we care more about value distance. And that's why our superpixels could be less regular. So they more fit into the value space. So that's the main idea of the SLEEK algorithm, and this is how we can basically divide our space into those superpixels, or make this over segmentation process. And what's really good is that this algorithm, as I mentioned, is quite popular, not only in image processing analysis, but also in GIS. And that's why it has been implemented in several GIS software, including GarageGIS, Saga, or Google Earth Engine. However, the main algorithm, it was aimed basically at images, and that's limitation if we think about spatial data. Because in principle, we can, with this algorithm, we can work on three-dimensional space, so this RGB space or maybe lab space. We could also work on one-dimensional space, so we could have just one value, one variable, and use this variable to create our superpixels. However, this algorithm is based only on Euclidean distances. So not only in terms of space, but also in terms of values. So if, for example, if you want to compare proportions or some kind of distributions, you only can use Euclidean space. However, Euclidean space is not always the best solutions if you think about different possible variables that we can use in spatial data. And that's why in the last few months, I've been working on a new R package, which tries to, on one hand, gives this SLEEK algorithm for people who work in R and opens this possibility. But on the other hand, for me, this package is also a way to work on how we can extend this SLEEK algorithm. And the main idea here is that we can work with one variables, we can work with many variables, we can work with so-called spatial patterns. A little bit more about that in a few minutes. But here we have more control over what are the distances or the similarity measures between our values. And the package is not yet on Suran, but you can easily download it from the RUniverse server. And I've put all of the instructions in the Mattermost channel, so you can look how to install it. And as I mentioned, this package is in fairly early stage. So I look forward to any ideas, comments, suggestions, bug reports, and it could still change quite a bit in the future. So let's start with the basic premise, the simplest example that I came up with. So here, like always, we start with attaching some R packages, and we will try to create superpixels, but just based on one variable. So in the supercells package, we've got volcano, TIFF, example data, which is just an elevation model. So in this example, we just want to create polygons or superpixels with similar elevation values. So let's maybe move to RStudio for a second, and let's try to run this code and look how it works. So we need to start, of course, by attaching our supercells package, but also Terra, because it accepts Terra objects as inputs. And the outputs right now in the current form are the SF objects. So our elevation data, and now that's all, because the main idea of this package is that most of the time, if you want to provide some other types of data or preprocess your data, you should do that before. But in this example, I assume that's the data I want to work with. So to create superpixels, I need to use the supercells function, provide my input raster data, and this input raster data can have one variable or one layer, but it could have several layers. It doesn't matter. And next, those two parameters. So k is the S parameter from the presentation. So this is the or similar. It's actually k is the number of output superpixels. So how many superpixels I want to have as the output, and compactness is the this proportion. So how much impact should have the spatial distance versus the value distance. And the whole processing of this function, or most of the processing, is done in C++. So it's, as you can see here, is fairly fast. We've done 10 iterations, and by default, it also cleans the data. And now we can see the output. So the output is if you open the file, it's basically an SF object with 49 super pixels. We wanted 50, but 49 is because we done some merging at the end, and we also needed to put them regularly before. And each of these polygons, or these superpixels, they are described by several values. So the first value is the ID number. The next two values are the centroids. So what are the centers, the final centers of each super pixel? And next, the last one is an average value for each region in our data. And you can see that it's done a fairly good job when we have lower elevations. We have one zone. If we have higher elevation, it's another one. And if there is something in between, we also have superpixels in between. And now we can try different parameters and look how our different parameters impact the results. So we can start by, for example, increasing compactness. So by increasing compactness, we are putting more emphasis on spatial distances. And now you can see that instead of highly irregular superpixels, now some of them are more square-like, and this is how we can impact this value. And the second main parameter is the number of superpixels, or alternatively, what's the distance between them. And if I change the value from 50 to 500, so I increase the number of my superpixels 10 times, you can see that now our area is covered by a large number of superpixels, or a large number of polygons. So this is how we basically can control the result. So this is the fairly easy example, just using one variable. The second example is also fairly straightforward, because it's similar to how this algorithm and this idea was developed. So here we have an image. This is a orthophoto map with some empty space. So this is missing data, just to test if our algorithm works on missing data. And our main goal is to divide the space into, in this example, similar objects. And in this case, our objects could be buildings or roads or grass areas and such. And this data is also included in the package, so I assume that all of you can read the data. And now I changed some initial parameters. I increase the number because this area is also larger than the area of the previous example. So I increase the area to 2000 and put the compactness value somewhere in between on 10. And I will explain this last parameter in the second. So let's just run the code. You can see we've done, again, 10 iterations. And our output is very similar to the previous one. In this case, that we still have polygons from the SF package, but we not only have IDs and coordinates of the centroids, we have averages of every variable. Because in terms of our satellite data, we have 3 variables. So those variables represent red, green, and blue bands. So that's why we also have average values for 3 bands in our output object. And here you can see, going back, that we have one additional argument here. And this argument is called transform. And this argument transform to lab basically means that we are not performing this algorithm on the raw RGB data, but we are transforming our data first to the LAB color space, because LAB color space works better with Euclidean distances. And that's why we could get better results. So let's look at the results. So this is how our results looks. So hopefully you can see that our field is now divided into many superpixels, similar to the stands and similar to some trees, and buildings have different, and roads as well, they have different superpixels. What's really great here is that this output is just our original image with the borders of superpixels imposed on them. But what we can also do is that we can create simplified images based on our results. So on the top here, we've got actual true image of this area with our superpixels imposed, while on the bottom, we just use the superpixels, and each superpixels is colored based on the average color of it. So what I've done here, I just wrote a fairly simple custom function to go from RGB to hex, because to plot, I need to have the hex representation, the hexagonal representation. And this way, I just took those 3 columns with average RGB colors and converted them to hex values. And finally, I used the hex values to create the map. So I can show you here. So this is my function. And now I can plot my area using the average colors. And hopefully you can see that this looks very, very similar to our original image. But there is one important difference. And the difference is that our original image contained 200 rows and more than 400 columns. So our original image contained more than 87,000 cells, while our new image, so this is our original image, 87,000 cells. And our new image, this one, it only contains as many images as we have, or as many objects as we have superpixels. So it's only 1,700. So we are having 1,700, and previously we've got 87,000. So we are keeping most of the information, but we are having only 2% of objects to store them. So this is the the way how we think about the whole process. With the extension of this algorithm, we can go even farther to some more complex examples. So now we are moving to slightly more abstract example, because we are not talking about actual objects, but we are talking about similar areas. And this is New Guinea, the island of New Guinea, and some other neighborhood areas with simplified land cover data. So we have forest in green, we've got agriculture in yellow, we've got some grasslands in the south areas, and so on and so on. And here we are not focused on delimiting exactly grassland areas or agricultural areas. We don't care about that because this was already done. We want to have areas with similar proportions of different categories. So I want to have areas where agriculture is maybe 80% and 20% is forest. And I want it to be different from area when there is half to half, and so on and so on. So how can we do that? So for this purpose, we can use a package called Motif. This is also a fairly new package and that I've developed last year. And using this package, we can extract what's the composition. So in other words, what's the proportion of different land cover category in a dedicated window. So in this example, I put a window of 20, which basically means that I divide this whole area into larger grids of 20 by 20 cells. So this, now I just extract this composition for the whole area of New Guinea for my window of 20 by 20. And as you will see in a second, the output looks as follows. So this is a standard output from this package, which basically tells us what's the ID of our window, what's the proportion of missing cells in each window. And next, there is a column list with those proportions. And we've got 24,000 of those blocks. And we can easily move them into their separate columns with LSP restructure. So now each column is just a proportion of land cover categories. So for example, the first window, 87% of its cells are missing, but from the rest, we can know that about 57% is forest, the second category, and the rest, 42%, is water. And finally, we can add spatial information. We can move that into spatial data in form of the Terra object. And I can show you this object. This object looks like this. So it has ID, proportion of missing cells. So you can see this proportion is the highest on the coastal areas. And next we have proportion of different land cover categories. And you can see here that the most dominant is forest. However, I don't care about IDs. I don't care about missing cells yet. I mostly care about the actual proportions. So I use the subset function to just extract the third from the third to the 9 layer in my raster. And now I can again apply the super pixels function. So with super pixels functions, you remember that we need to provide one or more variables in form of raster data. So here I've got 7 layers because each of the layers are related to the proportion of land cover categories. Next, I need to provide how many supercells or super pixels I want to have. I put 1000 in this cell, in this example, and I need to decide on the compactness value. And I'll tell you a little bit more about it in a second. But here, now we can also move to use other distance functions. Because Euclidean distance is not perfect when you have proportions. There are better measures here. And one of the measures that we can use here is called Jensen-Shannon distance or Jensen divergence, that we can use to better compare proportions of different land cover categories. And what's important here is that this distance is only used for the distance between values, but we are still keeping the Euclidean distance as a spatial distance. And therefore, our compactness should be, the value should be of compactness should be adjusted to that we have changed the distance function. So now you can see that the function runs quite fast on the data of this size. And again, we are receiving our data in forms of the ID, X and Y's, so coordinates of the centers. And next we have several columns, 7 columns with the average proportions of land cover categories. So this is our output. And just to maybe highlight you a few things, or maybe you can do that on the slide. You can see that some areas, for example, here, are very or fairly homogeneous. So this is that grassland area, or this agricultural area is fairly homogeneous. But in many places, our superpixels adjusted to local areas. So for example, here we have a mix of agriculture and forests. And similarly, we have got it here on the coast when you have mostly agriculture with some forest, which is different from mostly forest with some agriculture. So those are 3 fairly basic examples of how you can apply this idea to different types of data, but the possibilities are not very restrictive, because in this package you can use about 50 different distance measures, and you can also use several averaging functions. Because, for example, for all of those examples I've showed you, we used arithmetic mean as an average. So our new centroid is just a mean of previous values. But in some cases, for example, you would prefer to use median, and that's also possible using this package. All right, so let's go to next topic. And the next topic is how we can obtain quality of our segmentations. And we could do that probably in many ways, and there are several techniques that are possible. And I'm just showing you 2 possible approaches for calculating quality, but there are many other ways you can do that. So here I've got 2 data sets. On the left, we've got the result of our segmentation. So those are our superpixels from 20 minutes ago. And on the right, we've got a new external data. Maybe those are some manually drawn zones, and we want to compare them, how our 2 maps are similar or how they differ. And one possible approach is to use a package called SABRE. So SABRE stands for Spatial Association Between Regionalizations. And the role of this package is basically to compare 2 maps with each other. And those 2 maps could be either vector maps or raster maps, but they need to have some zones or regions. And the main function in this package is called vMeasureCalc. It takes our 2 data sets, and it takes also names of columns with IDs. And the result looks as you can see here on the top left. Basically, we've got three values. V-measure is the overall similarity between regions, with the larger being it's the more similar. Homogeneity is relation between the how best our first map fit inside the second map, while completeness is the opposite. So how the second map fits well in our first map. And again, if the value is closer to 1, which means that our maps are more similar to each other. So those three values are the global values of similarities, but we can also have local values of similarities. And the first one is how we compare our first map to the second, and the second one, how our second map is homogeneous in terms of the first map. And we can see area by area how they are similar or how they are different. So this is quality when we have external data. But what can we do if we don't have any external data? We just want to calculate some internal quality metrics. Then there is also a new approach of mine to work with that in the form of the package called regional. And the main idea of this package is to calculate how cells inside of our regions or superpixels are similar to each other, and how the pixels inside of our region are similar or dissimilar to other superpixels. And we can have several metrics. I will show you just two. So inhomogeneity means how dissimilar internally each superpixel is. And isolation means how our superpixel is different from its neighbors. And to calculate this, we just need a function called RegInHomogeneity, which takes our superpixels or any other polygons you have. It's not only limited to superpixels. And next, it requires our input raster. So you can see our original data on the left and the values of inhomogeneity on the right. So you can see that most of them inhomogeneity is quite low. So this means that they are fairly internal, similar to each other. But there is one superpixel here, which is quite inhomogeneous. And you can see here why is that? Because it's some cells here are on elevation of, let's say, 130 meters, but some cells are less than 100 meters. So that's why this one is not homogeneous enough. And if we look at this data, we can think, oh, maybe I need to create more superpixels to decrease inhomogeneity. And the second parameter is isolation. So isolation stands for how our area stands out from the neighborhooding areas. And here you can see that this one stands out the most because it's fairly different from, let's say, this one and this one and this one, because it has mid values of elevation. And this could help us maybe as a next step to merge some superpixels which are neighbors and are fairly similar to each other. So this could help us in some post-processing steps. And about post-processing steps, I can also show you one example of some post-processing. So going back to the second example for our RGB image, we've got our super pixels representing different objects. And now I maybe want to group them. Maybe I don't want to have this field as 20 separate superpixels. I want to have them as one super pixel or one region or one object. So one possible approach here is just to use some kind of a clustering. This is one of the simplest approach, actually. And before doing that, I think that it's better to do that in LAB color space. So that's what I do first. So first, I convert my values for each average values for each superpixel into from RGB to LAB color space. And next, I use this color space or those values and I apply a hierarchical clustering to them. So first, I just apply hierarchical clustering that you can see on the right. And I decided based on this dendrogram that I want to have maybe 13 separate clusters or categories. And you can see them here that we've got 13 different categories. And of course, I can do less and more if I want. And this is our result. So here, each color represents different hierarchical cluster obtained from hierarchical clustering. And you can see, for example, that our field is the 13th cluster. So now what we need to do, or what we can do, is to, first of all, use those clusters and put them as a column in our SF object. And next, we can do some spatial operations on our SF object. So here, I'm just dissolving borders between my clusters. So instead of having 20 polygons for my field, I have just one. But this could also combine disconnected areas together. And that's why I'm splitting disconnected polygons into separate areas. And here you can compare the original, our first output, so the superpixels. And on the right, we've got clustered superpixels. So I dissolved all of the borders. And you can see that right now, some areas like the field or the surrounding areas or the grass areas or trees are delineated quite nicely. And of course, again, by changing the number of clusters, I could improve this result. Okay, so this is more or less I wanted to show you. So just a few summary points. First main point is that the whole idea that I showed you here is related to spatial segmentation. So we want to create groupings of cells with similar values. And those similar values could be objects like buildings and roads, but they could be also some more abstract ideas like proportion of land cover categories or similar ideas. They could be also time series of spatial data. And the ideas that I showed you are implemented in a few packages, but the most important here is the supercells package that allows us to create superpixels using any defined distance measure, average function, and any number of variables we wanted to use. And of course, with R, as always, we can pre-process or post-process our data if we want to do that. And the last point, a last important point is that this is still work in progress. So if you have any ideas, comments, suggestions in terms of the whole idea or in terms of the code or the package, I will be very, very happy to hear you, and they will always be very important for the direction of the development. On the right side of the slide, you've got some links. And I've shared the slides on the Twitter and on the Mattermost, so you should be able to look at them every time you want. So that's all from me. Thanks.
All right, thanks a lot, Jakub. Yeah, we have 10 minutes left for question, and there are some posted on Mattermost. I start at the beginning. So the first question, or there are actually some questions that are quite similar. One is, can the initial cluster centers be distributed randomly or in a different way than regularly? And a similar question, could randomly distributed supercell centers improve the clustering, maybe even weighted to target highly heterogeneous areas?
So the standard algorithm of the superpixels, due to the time, I simplified that, but the standard algorithm works in this way, that it starts with the regularly spreaded centers, but then it tries to go into very small local window to check what are the for example, we can for example, by having them regularly, we can go to the only cell which is very different from the neighbors. So the first step is to find the homogeneous local window. What's the most homogeneous cell in the local window? So basically, it's not regular, but it's fairly similar to the regular. And in the current form of my package, it works in this exactly the same fashion as in the original implementation. However, if some of you think that it could be useful or important to have the option of having them differently, I don't know how it will behave, but it's maybe this could be a good thing to try. So I can add this option to maybe specify your own centers as SF object or as data frame with coordinates.
Okay, then we have a question. The Mahalanobis distance is not included. How could it be added before waiting for update of the philanthropy package?
Long story short, when I started this maybe let's go here. Here you can see that we've got the dist_fun function, and in the current form, we've got three options. The first option is to provide a name of one of the built-in distance functions. And there are only three: Euclidean, JSD, and DTW, so for dynamic time warping. So that's first option. And if you use this, it goes to the internal C++ code for the calculations. It's the fastest. The second approach that you can use is 46 different distance measures from the philanthropy package, and it is already implemented in this supercells package. So you can use that already if you just install my package from the RUniverse website. It will also install the development version of the philanthropy package with those 46 distance measures available. But there is also third option. The third option is that here you can provide your own function. So instead of string or text, here you can just provide a function which takes two values as an input and returns one numeric values as an output. So even if you have your own distance that only you know and only you use, you can still use this distance in this package.
All right, next question. Is it possible to force the number of superpixels so that none of them will be merged or removed during cleaning? For example, in the first example that you showed, 50 were specified, but 49 ended up being created.
Yeah, so maybe I'll show you the documentation of the function to just clear two things. So in the examples what I showed you, I used the K number. So the K number is the number of expected superpixels. And try to imagine if we have a square, and I want to have 25 superpixels. It's easy, just 5 by 5. But if I want to have 26, it's impossible. So that's why we won't have 26 if we provide 26 for the square area. There is also a second option, which is alternative option to the K1, which is called step. So you can provide what's the distance between each superpixel. So you can still use either K or step to obtain that. But going back to the first part of the question, you can also control for the cleaning process. Because by default, there is argument called clean, which equals to true. So by default, we are applying this cleaning process at the end, but you have two options. The first option, of course, is to just get rid of it and say, I don't want to do cleaning for me, I will do that myself. So you can just change that to false. But there is also a second option called mean area. So if this option is true, you can specify what's the minimum possible area of my output superpixels. So for example, if I want to have very small superpixels, maybe of 3 cells, 3 raster cells, that's fine for me. I can specify mean area equals 2. And this will remove only single superpixels and superpixels with containing 2 cells. So that's this way we have quite a lot of control over not only the number of superpixels, but also how they are post-processed.
Right, thank you. So the next question is, could placing the initial superpixel centers in a hexagonal grid, could that increase the compactness of supercells in homogeneous areas?
Probably. I think it was not idea in the original paper, but I've seen it's implemented. I believe in GrassJS. So the slick algorithm in GrassJS allows to decide if we want to start with a regular grid or maybe hexagonal grid for our centroids. And probably if we use hexagonal ones, we could slightly improve the results. It's not implemented yet here because I try to prioritize stuff. So I prioritize those different distance functions. I prioritize quality control, but it could also be done. And if any of you want that to have, just open a new issue on GitHub.
Okay, next question is, can we apply the supercell method to meteorological variables?
Yeah, like the main idea of the whole project is to generalize the original approach to as many applications as possible. So as I mentioned, you can use dynamic time warping as your distance function. So for example, you can have a time series of temperatures as your variables. As long as your layers are the temperature layers, so let's say you've got 12 layers for each month, you can still apply the supercells function.
Okay, so the next question is, have you compared using supercells with the traditional land use classification methods, for example, random forest or support vector machines? Which one performs better on, say, for example, Landsat data?
I have not, but I've seen some papers doing similar things. So there are some papers doing segmentation for land cover classification using the slick algorithm as well. So you can look for the papers doing that. Maybe using different distance functions and different variables could improve that, but I don't know.
Okay.
Worth to try.
All right. Next question regarding Sabre or Sabre, I missed the pronunciation of that. Would it work to evaluate the quality of object detection that do not segment or partition the image, for example, road or building detection?
Yeah, so as long as you have the true polygons, let's say, of objects, also those buildings and roads, and you have your classification of space, you just need to have either two polygonal vector data sets or two raster data sets, categorical raster data sets, and the idea should work.
Okay, last question, because we don't have much time left. Is there a way to take into account the data distribution?
Not in the package itself. So if you want to take the let's say that your data is queued or something similar, you can pre-process your data first. So instead of creating segmentation based on the raw data, you can maybe create segmentations on the logarithms of your variables or some other pre-processed values. That's the role of the R spatial packages, and I'm not going to re-implement the things that already exist in R packages like Terra or Stars.
Okay, then there's one question left, but I think we don't have more time. So Jakub, probably you can...
we don't have time. I'm sorry. We don't have time, so we have to stop.
Yeah, then thanks again, Jakub, for that great presentation. And I think we have now a break again of 15 minutes.